All right, let's talk about bias and mean square error. So if we use the quantity theta hat, for example, as an estimator for a population parameter called theta, now, I mean, what is theta? I don't know. It could be anything, okay? Maybe theta is the actual population mean. Maybe theta is the actual population variance. Maybe it's the actual population maximum. Okay? It could be anything, any attribute of the population. But you can't know it for sure. So what do? You have to take some data, and then from that data, you're going to compute something that we call it theta hat that you use to estimate theta with. Okay, so the bias of this estimator theta hat. We saw this. You can see this in the preliminary set of notes. But the bias of that estimator is defined to be. It's defined to be the difference between the expected value of the estimator and the actual parameter. Okay, right. So, and I had this kind of a picture again, in the preliminaries notes. But maybe this is the actual parameter value if you want to think about vectors or something, or some kind of a target. But you don't ever actually know it, so you take a stab at it. Okay, over and over and over. You have this estimation procedure. You take a data set and you estimate. There. Your buddy takes a data set and his estimate is here. Okay, so there you go. Okay, on the average, maybe this right here, that maybe this point is the expected value of your estimator. Okay, kind of liken this to target practice. If you ever shoot, maybe this is the bullseye. You're shooting for here, but you've got a rifle and you're taking shots and you're aiming for this point, but you never quite hit there. You're all over here somewhere. Okay, so you have this notion of accuracy and precision, right? Accuracy is sort of has to do with is the point cluster centered there. You can think of having a high degree of accuracy as having a small bias. In this case, you have some bias there, right? The bias of theta hat is equal to the expected value of theta hat minus theta. It's sort of this difference right there, the difference between the expected value of theta hat and theta. There's also some degree of precision. The precision is like the variance. Okay, is the point pattern spread out about its mean or not? Okay, what you really like is for a what you really would like to have is not only a high degree of accuracy, so that you have points clustered about the actual deal there, but also a high degree of precision, so that they're very tightly clustered. Okay, this sort of indicates a lot of accuracy and a lot of precision. This indicates maybe not so much of either. Situation like this sort of indicates maybe there's some accuracy there, but there's my theta, there's my actual parameter, but it's not very precise. Okay. On the other hand, if you go to the rifle range and if you might like to see this kind of thing. It's not very accurate, but it's very, very precise, right? Maybe that just means you need to make a simple adjustment in your sights to move this, and you can remove the bias. But anyway, so there are a lot of attributes that we like to talk about estimators. We like estimators that have little bias and also that have little variance. Okay, but for now, let's talk about the bias of, say, the sample mean. It turns out the sample mean, the random sample mean, which we'll define to be as 1 over n times the sum. Goes from 1 to n of your random data values. This is an unbiased estimator for the population mean. Here's the proof. Okay, it's pretty easy. I just have to show that the expected value of the sample mean is indeed mu. Okay, well, the expected value of x bar is, I'm just going to fill in here, x bar is equal to that the average of the xi values, right? Now it turns out, remember when you take the expected value of something, it's really the sum of these things weighted against the probabilities, or the integrals of those things, right? So when you do that, it actually, you can pop this is a constant, right? You can pop that out of the summation, get 1 over n times the expected value of the sum. Now it turns out, and we said this before, it's true, that the expected value of a sum is the sum of the expected values. Okay, that just follows from properties of summations and integrals, turns out. But so I can write it like this. Okay. Oops, 1 to n. Now, what's the expected value of one of those observations? Well, by definition, it's just the population mean, right? Okay. This is just another way to write the population mean. And so this is just 1 over n times, now I'm summing up mu's, right, from 1 to n. How many of them? I've got n of them. I'm summing up n mu's. The n's cancel, and this is just mu. So yes, in fact, the expected value of the sample mean is the population mean. That means the bias, this means that the bias of the sample mean is 0. That's nice. So it's an unbiased estimator for the population mean. Okay. Now, while unbiasedness is an attractive property for estimators to have, not all estimators are unbiased. It turns out that the sample variance, okay, if I take the square root of both sides here, you'll see that you get the sample standard deviation. But the sample variance is an unbiased estimator for the population variance sigma squared. Okay, and what makes it unbiased is the fact that we're dividing by n minus 1 here. It turns out this quantity, if I don't divide by n minus 1 outside there, if I just simply take the actual arithmetic average of the squared deviations from average, it's no longer equal to the actual population variance on average. Okay, the bias is this. In fact, you'll show this for homework. It's pretty easy. Okay, and again, like with all the homework problems, if you ever run into trouble, don't spend 9 hours on your homework. Just let me know. We'll work it out. Or get with your classmates. Okay, so for another example, the sample maximum is a biased estimator for the population maximum. This should be pretty intuitive, right? If you have a population and maybe here's the minimum value and here's the max, if you take a sample from this population, maybe you get one of these and one of those and maybe one of those and one of those and one of those. The maximum from your sample is going to tend to be, well, it certainly can't be more than the actual maximum. It's going to tend to be less. Occasionally you might actually attain the actual maximum, but your sample maximum will tend to be biased. It'll tend to be a little less than the actual maximum. Besides unbiasedness, there are other attractive qualities estimators can have, like small variance we talked about, also maximum likelihood estimators, which we'll talk about later on, consistency, and so forth. And you can read more about these on the web or in a book like the one by Mendenhall, Wackerly, and Schaefer. But some of these qualities are beyond the scope of this course. We are talking about small variance and maximum likelihood for sure. But and so sometimes you might want to sacrifice one quality for another, but unbiasedness and small variance are very, very nice. And again, they sort of correlate to accuracy and precision interpretations. So they're very intuitive. An estimated regression coefficient, turns out, is an unbiased estimate of the parameter beta I. If the mean of all the possible estimates of BI equals beta I. So what does that mean? Well, you can think of taking a whole bunch of different samples and doing regression on all of those samples. So if you could do this over and over and over again, and always computing these estimates for these parameters in the model, the slope coefficient and the y-intercept, then on the average they would be equal to what they're supposed to be. Okay, then those things are unbiased. So the predicted response, yi hat, is an unbiased estimator for the mean mu I if the mean of all the possible predicted values actually equals mu I. And so again, by this Gauss-Markov theorem, you can read more about it in your book. The way that we estimate the y-intercept and the slope, given those previous expressions, are attractive estimators for the actual intercept and slope if you could get all of the points in the population, because they are in fact unbiased estimates, and they have the smallest variance among all unbiased linear estimators. So you can think of it as our b naught, which is y bar minus b1 x bar, and b1, which is r times sy over the standard deviation in the x values. These are both, what that says is they're both as accurate as possible, meaning bias equals 0, and have as good a precision. Is that, I'm not sure if that's very good English there, but they have the best precision you can get. Best precision you can hope for among all estimators with zero bias. So for all the estimators with best possible accuracy, they have the best possible variance, smallest possible variance, or smallest or best possible precision. Now, total mean square error. We saw that this was also in the preliminaries. It turns out total mean square error for an estimator is the expected squared deviation of that estimator from the true thing that you're trying to estimate. So maybe if I have this picture again, maybe here's some estimates for theta. Okay, and the mean square error is sort of the expected squared deviation. If I take these are my deviations. Okay, if I did this over and over and over and over and over and over a million, billion, trillion times, all right, and I found all these deviations, and then if I squared them and averaged them, okay, so really you have these squares here. See that? See how messy this is going to get? So forth. Maybe I'll do another one there. Okay, if I square all of those and average them, that gets me the mean square error. It's some sort of measurement of overall variation off of what we're trying to estimate. It turns out, and in fact you can do this for homework, you will do this for homework, that the mean square error of our estimator partitions nicely as the sum of the square of the bias and the variance. And again, so this is really nice because it says that this overall sort of variation measurement of our estimator off of our population parameter that we're using it to estimate is sort of a sum of an accuracy measurement and a precision measurement. Okay?